What I'm wondering is, does this collection of 4 vectors form a basis for 4-dimensional space? Is this collection, which I'll call B, V1, V2, V3, V4, a basis for our 4-dimensional space? Because I picked the vectors at random, in all likelihood, the answer is yes. Unless I'm very, very, very unlucky. I feel confident in assessing the probability that it's a basis to be 1, or at least 0.99999. I'd be willing to bet a lot of money that it's a basis. If we think it's a basis, and if we're trying to show it's a basis for 4-dimensional space, how would you verify that? There's 2 conditions. Do you remember what they are? I'm just going to go ahead and say the answer is yes, but maybe there'll be egg on my face and the answer will be no. To confirm this, what do I need to do? It is related to putting them in a matrix and doing row operations, but describe the properties that they need to have in words. I need to show this is a linearly independent set. B is a linearly independent set. And I also need to show what else? Yeah, I need to show B spans R4 notationally. R4, all of 4-dimensional space, is the span of those 4 vectors. B is a collection of 4 vectors, just 4 vectors. But when I put the word span in front of them, unless those 4 vectors are all the 0 vector, this is always an infinite set. Because by definition, what span means, it's the set of all linear combinations of the vectors. This, by definition, is the set of all linear combinations of those vectors. X1 times V1 plus X2 times V2 plus X3 times V3 plus X4 times V4, with the property that each of these X's, X1, X2, X3, and X4 are all real numbers. I'm out of space there, that's why I'm writing it that way. Those are all real numbers. Now it's possible, not likely, but possible that it's not a basis. It's possible that it's not a linearly independent set. It's possible it doesn't span all of R4. It's possible this set doesn't equal every vector in R4. Just not likely. Most likely the answer is yes. Again, I was willing to bet money, so I went ahead and wrote that down. I'm not literally betting money. All right, but this begs a question, how do you do these things? To show B is a linearly independent set, I need to show that the only way a linear combination of these vectors equals the 0 vectors equals the 0 vector is if all the weights are 0. I need to show that this vector equation, x1 plus, times v1 plus x2 times v2 plus x3 times v3 plus x4 times v4 equals the 0 vector, has only the trivial solution. All the x's are 0. i.e., if I put those x's in a vector, the only solution is the 0 vector. It's a trivial null space, trivial kernel for a linear transformation. Yeah, if I made these vectors the columns of a 4x4 matrix, that would define a linear transformation. And if they're linearly independent, that linear transformation is going to have trivial kernel. It'll be a one-to-one function. All these things are related to each other. It's just different ways of thinking about the exact same thing. That's what I would need to show it's a linearly independent set. To show it spans R4, I would need to show that given any vector B in R4, this equation, x1 times v1 plus x2 times v2 plus x3 times v3 plus x4 times v4 equals B, has a solution. At least one solution. In other words, the corresponding linear transformation is onto. If V1 through V4 form a linearly independent set, the corresponding linear transformation is going to have trivial kernel and be one-to-one. To show B spans R4, the corresponding linear transformation is going to be onto. The image will be all of R4. The column space of the matrix will be all of R4. Can I do all this, both of these steps, at once? At least with Mathematica you can. I'm not so sure about a calculator. I can make an augmented matrix where the first 4 columns are my vectors, and the last column is, say, an arbitrary 4-dimensional vector, call it A, B, C, D. And I can row reduce to reduce row echelon form and see what I get. I'm betting, without literally betting, that I will get this identity matrix for the part to the left of the dashed line and some particular expressions to the right that I'm not going to say what they are because it's too hard to do in my head. Question? Oops, 1. Thank you. And if that's what happens, which again, I'm betting without literally betting, if that happens, that has verified both of these, because if all these numbers are 0, if it's a homogeneous system, I'm gonna get a bunch of zeros there, actually. These stars will be 0, I'm betting, when A, B, C, and D are 0. So x1 will be 0, x2 will be 0, x3 will be 0, x4 will be 0. And if these things are not 0, I'll still get something over here that will involve A, B, C, and D. All right, let's have Mathematica do it. Calculator can handle arbitrary A, B, C, and D, but Mathematica can. I was a little unsure about whether it could this morning, so I tested it. It worked. So I'm going to do matrix form. Again, matrix form just displays the output as a matrix. That's all it does. It's a little small. Matrix form, row reduce, my augmented matrix of interest. A itself is 4 by 4, but I want an augmented matrix, so I need 5 columns, 4 rows. And now I'm just looking at these vectors down here. Let's move this down and this up so I don't get in the way as much. 1, 0, 2, -6, A. I looked at the first components there, and then an A. Second components, -1, 4, -5, -3, B. Third components, 2, 5, 7, 0, C. Fourth components, -3, -2, 8, 4, D. So unless I'm very unlucky, what I said will happen will happen. Yep. There's my identity matrix. Dash line here. Here are my expressions involving A, B, C, and D. Very complicated expressions. But they are definitely expressions that are 0 when A, B, C, and D are all 0. That's enough to say that the column vectors of the original matrix are linearly independent. And, well, they are defined. They exist for any A, B, C, and D. That's enough to say these column vectors are, that they span R4. Right there. And that's enough to say these 4 column vectors form a basis for R4. Should I say it again? Linearly independent, because if A, B, C, and D are all 0, then these numbers are all 0. Spans R4 because no matter what A, B, C, and D are, there's a solution. Complicated solutions, but they are there. By the way, you see those fractions with big denominators, 831, 554, 1662. I'm guessing perhaps the determinant of the coefficient matrix might be 1662. Let's just see if it is. It will be non-zero because we were able to do all this. I just copy and paste this. Never tried this. Hey, yep. Hey, yeah, negative 1662. Non-zero, so that's another reason why all this works. Can we save work here at all? Well, I mean, I really did it as pretty efficiently as possible, really, by just doing one row reduction and then explaining. There's another way to think of it efficiently. There's something called the basis theorem. Basis theorem that relates a set like this being a basis to the dimension of the space. Let me just say it verbally. I'm not going to write it down. So R4 is a four-dimensional vector space. Any basis of R4 will have four vectors. The standard basis, the simplest basis, is first vector 1, 0, 0, 0, second vector 0, 1, 0, 0, third vector 0, 0, 1, 0, fourth vector 0, 0, 0, 1. The columns of the identity matrix is the simplest basis, sometimes called the standard basis. But any other basis for four-dimensional space will have four vectors in it. And the basis theorem then implies that if you've got a collection of four vectors in R4, for example, a four-dimensional space, and you know it's linearly independent, it will automatically span. And vice versa. If you know it spans, it will automatically be linearly independent. That's the basis theorem. Something to watch out for. Something else to watch out for to close out class today, and we're getting already late, so I think we'll just end class after I show this to you. So I'll stick around if you want to answer any questions. Is something called coordinate vectors. Anytime you have a basis for a vector space, whether that vector space is R2, R3, R4, or a more abstract vector space, maybe a vector space of polynomials, I talk about those in the lectures. Anytime you have a finite basis for a finite dimensional vector space, you can create what are called coordinate vectors. What is a coordinate vector? When you're trying to solve an equation like this, given an arbitrary b in R4, and you try to solve this equation for x1, x2, x3, and x4, based on v1, v2, v3, and v4 being a basis, so you will be able to solve such a thing, the x's are related to b, and if you put those x's in a column vector, it's called the coordinate vector of b. Maybe I shouldn't have used the letter b here. In this context, with that letter, the coordinate vector of b written b inside square brackets sub b. The fact that there's two b's here now makes me wish I had chosen a different letter here. This little b is an arbitrary vector in R4. This capital cursive B is a basis, not a vector. This, by definition, is a column vector with the x's as the components. Whatever those weights are that solve this equation, those become the components. Take an example, take a particular example. Go back to Mathematica here. let's say I pick the B to be, well, let's pick something involving 1662. 1662, negative 3,324, 0, negative 1662. If that's my B vector, I'm picking it so the answer comes out nice, hopefully. What are the X's? Those numbers. That is the coordinate vector for this vector with respect to this basis of R4. Say it again. This column vector here is the coordinate vector of this original vector with respect to this basis. Notationally, I would write, for this example, the coordinate vector of this vector 1662, negative 3,324, 0, negative 1662, with respect to my basis, is the other vector you see there in the row reduction, 1,026, negative 528, 84, negative 78. Now, careful, I'm not saying those two vectors have the same numbers. They don't. This is defining a relationship between these vectors, defined by the basis, effectively. Effectively, it's like a change of coordinates that transforms this vector into this vector in a possibly useful way. Let me say a few more things. Give me 2 more minutes here, okay? I know this is a lot to take in. There's a lot of topics in this class. Can't be avoided. Most of our differential equations examples we do are 2-dimensional, 2 by 2. Once in a while, we do 3-dimensional. I think maybe near one of the last couple lectures, I do a 4-dimensional example. If we were to consider a system of 4 differential equations and 4 unknowns, that it was a linear system where this matrix right here was the coefficient matrix, the capital A, to solve it with maybe the matrix exponential, like I talked about 20 minutes ago, we would need this idea of eigenvalues and eigenvectors that I keep hinting at, and ultimately a change of coordinates. The eigenvectors, in all likelihood, would form a basis for R4, not the same one as this one. And it would be those vectors that we would want to use as a new basis with a new coordinate system to change our coordinates to make the system easier to solve. That's the whole point. To make matrix X easier to calculate. That might not have much meaning to you right now, right? It's a big picture idea. It's going to take on meaning as you continue working through the content. In the book, in the textbook, our main textbook, they talk about eigenvalues and eigenvectors plenty in chapter 3. What they don't talk about, something you'll still need to know, is change of coordinates, bases, coordinate vectors, that kind of thing. The linear algebra content that I talk about in the lectures relates those to the eigenvalues and eigenvectors that you find in here. And that's where the course comes together best.